Okay, so let's talk about some remarkable things about parabolas and quadratics. So, well, this peak, this vertex, the x-coordinate actually has a formula, and I would like to jot it down here. So, the x-coordinate of the vertex is given by the formula the opposite of b over double the a, okay, as long as the quadratic is in the general form. So as long as y equals ax squared plus bx's plus c. So a number of x squareds, b number of x's, and c number of regular units, or whatever. Okay, so a little bit of a formula here. I realize that it doesn't seem important, but probably need it along the way here. Okay, another remarkable thing, the axis of symmetry travels through that vertex. Okay, so it's doubly important here. So the axis of symmetry travels through the vertex. Got it? And that means that it has the same formula. So that means the axis of symmetry is this vertical line with the same formula given by the x-coordinate of the vertex. So the axis of symmetry is a vertical line with equation so as long as you remember this formula, you get two for one there. Okay, so opposite of b over 2a, but again, that is just for the x, and now it's also the equation for that vertical line. And then a large remark here. So when I create a table of values, I like this. So this peak, this vertex, is in the center of my graph. So I like it to actually land in the center of my table and have points around it. Points above it, points below it, symmetrically, so that I can get the peak and symmetrical points on either side. So not only do I use it to find the peak, but I use it in my table of values. So when creating a table of values, for a quadratic, we use the vertex as the center point. Of the x's. This just allows us to get values of x and y on either side of that center point or that focal point, or it's not even that, it's called the vertex. So then we choose x values that are equally spaced around it. So then choose x values equally spaced on either side. So above it and below it. And in reality, it's x values, which means it's actually to the left and to the right of it. But when we see it in the table of values, it feels like it's above and below. Okay, so we do all of that with that vertex. Let's see example 3. Graph y equals x squared minus 4x's plus 7 by following these steps. Find the x coordinate of the vertex. Okay, well, right off the bat, I see that it is a quadratic. So it does have a vertex, but I want to label this. This is actually 1x squared, silently, implicitly. It is negative 4 x's and 7 units, whatever those are. Whatever our y is counting. Find the x coordinate of the vertex. Okay, I have my a, my b, my c, and I know I have this fancy formula that says x is equal to the opposite of b over double the a. Okay, so 2. 2 is the x coordinate of the vertex. Next, create a table of values around and including the vertex at the center. Table of values. 2 in the middle. Okay. Below that, 1. More than that, 3. Below that, 0. Above that. So now I have 2 in the middle, and I have equally spaced them on either side. Okay. Now I just need to find all of the y values that go with them. Well, here we go. I have to kind of write this down, my computations, right? So 0 squared minus 4 zeros plus 7. So 0 squared minus 4 zeros plus 7, I get 7. Plug in 1. So when x is 1, y is equal to 1 squared minus 4 ones plus 7. 1 take away 4. 4 ones is worth 4. 1 take away 4, we've got negative 3. Negative 3 plus 7, 4. Got it. When x is 2, 2 squared minus 4 sets of 2 plus 7. 2 squared is 4. 4 take away 8 is negative 4. Negative 4 plus 7. Wait a minute. Did I do some arithmetic wrong here? 4 minus 8 is negative 4. Negative 4 plus 7 isn't 4. It's 3. Oh, silly Abby. Got it. And hopefully these are going to be symmetrical. I bet we get 4 and 7, but we better check it. When x is 3, we have 3 squared, take away 4 sets of 3, and then add 7. 9, take away 12 is negative 3. Negative 3 plus 7 is 4, indeed. Okay. And just to finish this, to be thorough, when x is 4, we would have 4 squared, take away 4 sets of 4, plus 7. 16 minus 16 is 0. 0 plus 7, 7. Voila! We have the vertex in the center. So just to label this, so right here, that is our peak or valley. That's our vertex. And then we have some symmetry across it. Nice. Graph the parabola on the page of graph paper. Oh boy. I don't believe I printed any graph paper. Draw the axis of symmetry with a dashed line and put it here. Rut-row. Okay. I'm going to do this by hand because I did not print myself a page of graph paper because I forgot to. So hopefully you will. I'm going to try to draw a very good grid. My x's just need to go up to 4. My y's need to go up to 7. Okay. Can I do equal spaces? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Okay. That is actually 3. Okay. And so my y's went up to 7 and my x's need to go to 4. 1, 2, 3, 4. Okay, so I got a little out of hand here, but okay, fine. Unless we forget we always start at 0. Let's map. 0, 7. Done. 1, 4. Gotcha. 2, 3. That's our peak. And now we go with the symmetrical points. There is our parabola. Now I want to mention at this point in time that the peak is actually a smooth peak. Like a well-rounded or well-weathered rock. It's not a sharp peak. It is not a point, it's a curve like a hill. Yeah? Voila, put a sketch here. Done. Okay, let's talk about wind turbines. Got this from your book. The profit of a wind turbine company, Breeze-Zap, this is awesome, Breeze-Zap and Breeze-App, like a breezy app. Anyway, depends on how kilowatt hours are generated by their turbines. Right. So profit depends on, how much power you got. Let K represent the millions of kilowatt hours generated, and P will be the company's profit. Okay, so profit, kilowatt hours. And we have a full picture here, just so that we see what we're working with. And it looks like this line is 0. So I'm actually going to go ahead and do this thing and create a darker line there. So here at 0, this is their axis. So just so that you see what I'm doing, I'm just making this line a little bit darker for my own visual preference there. Yeah, so that I can see what is positive profit or debt. And how many? Millions of kilowatt hours. Okay. We're going to have to go back and forth between this and the questions. What is the p-intercept? Also known as the y-intercept. Write your answer as a sentence explaining what it means, what they mean. Got it. P-intercept. Okay, so certainly this axis is P. Okay, maybe I'll make that a new color. Green, perhaps. Oh, this would be hilarious. Actually, let's go like this. Green for above and red for below. Sorry if you're colorblind. Then that looks like just one large axis. The p-intercept, I see it right here. Okay. If this is 50,000, then it's counting by 25,000s. So what's half of 25,000? Like 12,500? So I'm thinking this is what? So take 50 grand and add to it 12,500, because it looks like it's about halfway between. I don't know, maybe around negative 62,500, something about that. Okay, so set this aside. Zoom out again. Okay, so I'm going to put P equals negative 62,500. Write your answer as a sentence explaining what it means or that means. Hold on. how many kilowatt hours is that? So the P is negative 62.5, but the kilowatt hours is 0. Okay, and so I'm actually going to put K equals 0 here. So when no, I forgot how to spell no for a second there, when no kilowatt hours are generated, so all of the wind turbines shut off, no kilowatt hours are generated, the company loses $62,500. Okay. Yep. So when no kilowatt hours are generated, so the turbines are off, the company loses $62,500. What are the K-intercepts? Ooh, it's plural. K-intercepts. Going back here, I see here's one right there, and here's another one right there. Let's zoom in on that business. All right, first of all, the profit is 0. Okay, and the millions of kilowatt hours, oh man, how many ticking marks is this? 1, 2, 3, 4, 5. Oh, it's counting by tens, so that's good news. So that's what, 10, 20, 25. K equals 25. And here we would go 400, 410, 420, 425. So 25 and 425. Okay, let's write that down. Okay, so K equals 25 and K equals 425 and P was 0. Describe what they mean in the context of this situation. Right. So, in order to have no debts and no gains in terms of profit and money, the turbines have to generate 25 million kilowatt hours or 425 kilowatt hours. So, in order to break even, no profit, gains, or losses, the turbines need to generate 25 million or 425 million kilowatt hours. Got it. Okay. All right, so break even, that's what we're going for. And it looks to me like we're going for in between there, yeah? How much electricity would be needed in order to generate, or in order to make, $100,000 of profit? Let's not get ahead of ourselves there or go nuts. So, 100 grand. I'm going to use this. You know what? I'm going to use blue. 100 grand. There is the 100 grand line. Okay, right there. And about right there. Okay. So I'm going to go ahead and look at how much kilowatt hours those are. That's 50, 60, 70, and 350, 360, 370, 380. 70 and 80. Got it. So 70 and 80. 380. So how much electricity would need to be generated? So either, what did we get? We got 70 kilowatt hours or 380 kilowatt hours. And that would bring us in $100,000 of profit. What is the most profit BreezeZap can make? How much electricity is that? Okay, so the most profit. Let's find this peak. There-ish. Something like that. Something about there. Okay, so let's see. It looks about halfway between. It's a little bit higher than halfway between. So maybe this would be, what is this? 225,000 and then, I don't know. Maybe 240,000. So roughly speaking, 240,000. Let's put that to the side. Oh, but I didn't check to see how much electricity that would require. So the most profit, about $240,000 in profit. How much electricity? Okay. Well, $200, $210, $220, $225 about 225. Whoopsie, million kilowatt hours. Ooh, whoa, I forgot the millions up here. That is a really big deal. Has to be fixed. Million. Kilowatt hours. And cannot leave this like that here. Got it. There's a really big difference between 380 and 380 million. Okay. Okay. This profit is modeled by the quadratic P of k equals negative 6k squared plus 2,700 k's minus 63,750. Write this with variables that can be used in your calculator. All right, so they're saying x's and y's. So this would be a y. Y equals negative 6x squared plus 2,700 x's minus 63,750. Got it. Use your calculator to check your answers for the last two problems. Ooh. Okay, this could be done a couple of different ways. First, well, for the last two problems, this is the vertex, yes? So just so that we're crystal clear, we could actually use our formula on it, which I'm just gonna check really quick to see if that's truly the vertex. So in terms of the vertex, without the calculator, the x value would be the opposite of 2,700 over double the a. Well, 2 times that is negative 12. So I'm just curious if we read the graph with enough precision. 225. Oh, la la la. So, okay, that is reassuring, yes, in terms of this. But now we're actually going to use the calculator, it says. I'm going to need that equation. Okay, so let's go to y equals. Let's clear out these other ones and put in negative 6. By the way, if you use the subtraction sign here, your calculator will be mad. X, and then the caret x squared, plus 2,700 x's, minus 63,750. Oopsie. definitely have a mistake there. Okay, now I have it. And it seems to me, maybe I'll use the window that they did on this graph. It looks like their x's went from 0 to 500. So I'm going to go ahead and hit window right here. X minimum, 0. X maximum, 500. The X scale, they counted by 50s. Got it. Y minimum, negative 100,000. Y maximum, 300,000. The Y scale counted by 50 thousands. Okay, and now I'm going to graph it. Okay, voila. And that looks pretty darn close to what, I mean, it just doesn't have the numbers on it, which is fine. But now I'm going to go ahead and go to second calculate. And we see a few things. We see value, we see maximum. So the first thing I'm going to do is actually go down to maximum. Okay. Left, so you want to arrow over. I'm using these arrows to go to the left of the maximum. Got it. And then it says to the right, so I'm going to arrow using this cursor over to the right side of what is the maximum and hit enter. And then guess, it doesn't matter, what do we guess? And here we see the maximum. Ooh, look at that. That is, round that to 225 millions of kilowatt hours and $240,000 of profit. That is precisely what we guessed based on just looking at the curve. Wow, what a good guess we had. And then I'm going to actually do this again. I'm going to hit second calculate. Oh, wait. You know what I'm going to do? I'm going to go to y equals and treat this like we did in the past and put in what, $100,000. And we can find the intersection. We go second calculate, intersect. First curve is blue, second curve is red, and the guess. So in order to get this intersection, you have to be near it. And it found it. Huh, what did we say? So this is saying about 72.25. Oh boy, 72.25. Yeah, we said 70 million kilowatt hours, but I feel like that's a pretty nice level of precision that we couldn't have gotten. Okay, let's do it again. Let's go second calculate, and let's find that other intersection. Okay, first curve blue, second curve red, and the guess. Now I need to go all the way over here. Enter. Okay, 377.75 million kilowatt hours. And we had picked, 380 and 70. We were very close. We weren't perfect, but we were pretty darn close. So in order to do this, so just to write down how we checked our answers, right? Okay. We used maximum, so first, second calc, or second trace, which is calc. We went to maximum, and we put in Y2 as 100 grand, and we went second calc and used intersect. Yeah, we were pretty close. 72.25 and 377.75. You know, pretty good guesses based on a graph at that scale. All right, so just to remember what we talked about in this section, right? We identify and graph quadratics from tables and equations. We found the vertex. In addition to that, we actually also talked about the axis of symmetry, but nonetheless, and we interpreted all of this information too. And I want to mention that when it comes to quadratics, remember, these tables and these equations, the tables, so the linear pattern was a first layer constant addition or constant subtraction. But the quadratics graphs were a second layer constant addition or constant subtraction. And we ended up having all of these different attributes for something that has this type of pattern, and we call it a quadratic